Okay, so now this is the topic 2 for noise control and room acoustic. So as per our first topic in which we were covering the light, we will be covering noise. So noise control and room acoustic is also one of the building services in a building lah. So for this topic, we'll be covering nature of sound, measurement of sound level, the attenuation of sound, noise, sound insulation, and room acoustic. So you have your core reading list, which is these two, Hall F and Greeno, and then McMullen. So this two is where all your lecture note is extracted from, all the information. And then additional reading material, and you have your finally your CLO. So CLO you'll be able to describe the characteristic of sound here, which is this in the building and environment, and then relate them to real situation. So there will be also a bit of calculation. So you have for this topic it will be related to CLO1 and CLO4. Okay, so as per usual, like the topic 1, before you know about the how noise is being controlled in a building, you first have to know the characteristic of a noise, of a sound, how they behave, how is it perceived. So when I say perceive is how do we recognize sound. So this is all the this is a direct characteristic of a sound wave lah. So sound wave is different from light. If it's a vacuum, then sound will not be able to travel through it. So how a sound is perceived is because of our brain. So if you do not have an ear and if there's not a living person, then we will not be able to perceive how sound is like. So sound is a transfer of energy from the vibration of a source. So without all this vibration, you will not be able to perceive this sound. So in a vacuum, there is no way to hear a sound. So sound can only be transmitted through solid, liquid, or gas. So in a vacuum, you won't have any sound lah. So the sound has a few characteristics. First of all, because it's done by movement of a state of either a solid, liquid, or gas. So it has a wavelength, it has a pitch, it has a frequency. So a wavelength is defined as the distance between any two repeating points. So in a undisturbed environment, which is undisturbed air, then the wavelength is a very consistent wavelength. But when it comes to sound, if sound were to interfere, then there will be a particular wavelength, which means that there's a movement of air in one wavelength. So this is something like an example lah. So there's a movement of 1 and 2, 1 and 2. So this is what it means by wavelength lah. And there will be a frequency. So with that, the frequency is the number of vibration that passes a point per second. So if an object produces sound wave that vibrate 100 times a second, then the frequency of that sound will be 100 hertz. So noise can be very, very high pitch or very low pitch, but us human, we only able to hear up to a certain amount of frequency. But for other animal, they will be able to hear even higher frequency lah. But as for us, there's only a certain amount of range that we will be able to hear. Like in the first topic in lighting, where we only be able to see up to a certain range of light. So for sound and a noise, the higher the frequency, the lower the frequency, then you hear a different tune of the noise. And if you were to notice in these slides, you have this sign lah for your from your mathematical, from what you learn from your maths lah. So a higher frequency will give a higher pitch, and a lower frequency will give a lower tune to it. And this is how the wave will be shown lah. And this is how the maths is related to the noise. Okay, so pitch is a frequency of a sound as perceived by human hearing. So a high pitch and a low pitch will give a different sort of noise that you'll be able to perceive. And you have your amplitude. So it's a measure of amount of energy in the sound wave. So a high amplitude means the sound will be very loud. If it's a soft amplitude, that means the sound energy is very low, and also the sound will be very soft. And finally, we have the quality of sound. So some sound are pleasant, some are noise. So a pleasant sound has a regular wave pattern, or their pattern is in a set of a set of movement. And so the pattern is in a regular set of waves, which is pleasant to our ear. But for a typical noise, then they are very irregular. So they move up and down and they do not have a very regular repeated pattern. So a pleasant sound is something that will go up and down in a very uniform way. But for noise, then you'll be moving up and down in a very irregular pattern. Okay, so since we know that sound needs to move in a state where there's some molecules, some like either solid, gas, or liquid. So if there's no such state, if it's a vacuum, then sound will not be able to travel. So to measure the movement of the sound, you'll be able to use this formula, which is the velocity of sound. So velocity is the distance moved per second in a fixed direction. So it's measured simply in meter per second, m over s. So depending on the material, the velocity of the sound is different. So in air, at a low temperature, the sound won't be able to travel as fast as in a solid state, which is a granite, steel, or glass. So this three is all solid, and the top two, this is a air, and liquid is a water. So as the material gets more and more dense from air to solid, the typical velocity of, which means how fast the sound move from point A to point B, or how fast the sound can be transmitted, is actually increased as the density increase. So why is this the case? Is because of how sound is being transmitted. So as with previously, I've explained that sound is transmitted through the movement of the molecules. So because of that, as the material the sound travel to, become denser, then the faster the sound is being transmitted. So we have this very simple formula, which is the lambda equals to the velocity divided by the frequency. So this is how you get the velocity of sound. So this velocity of sound is independent of the rate at which the sound vibration occurs, which means that the frequency of a sound does not affect its speed. So it is unaffected by variation in atmospheric pressure such as those caused by weather. So an example of how you use the formula. So a particular sound wave has a frequency of 440 hertz and a velocity of 340 meter per second. So you have to calculate the wavelength of this sound. So with this formula, you want to find out what is the wavelength. So you are just required to move this frequency to the other side of the equation. So as per here, so you're given your velocity, which is meter per second, and the frequency. So using that formula by moving around the variable, you'll be able to get that the wavelength for this particular sound wave is 0.77 meter. So sound, besides the basic characteristic of sound, because of the way they travel, then sound emits resonance. So every object has a natural frequency, which is the characteristic frequency at which it tends to vibrate when disturbed. So a resonance occurs when the natural frequency of an object coincides with the frequency of any vibration applied at the object. So what this means is that at a particular frequency, then it will be amplified. So the result of a resonance is extra large vibration at this frequency. Which means when a sound wave is being applied, then if 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 it's happening at a correct frequency, then the sound will harmonize and cause a bigger vibration. So an example is the swinging of a suspension bridge can resonate with the footsteps from walkers, causing it to feel at this frequency, which means that at a normal this suspension bridge, if it were to move up and down and it were to harmonize, which means the swinging of the bridge of going up and down is harmonizing with the footsteps from the people walking on top of it, the frequency will increase even more, which means it will swing up and down even more. I wonder if there should be a video, so let's look at it. Okay, so this is from London, UK. So this is an example of what will happen if there's people walking on it and then the bridge isn't built up to par lah. So in normal days they will wobble, but when people are walking on it, then they will wobble more lah. So if you can see from the video, bridge as is as it just described shouldn't wobble so much, shouldn't move so much. There's been a lot of example on case of this sort of things that happen.
This bridge was exceptionally down vibrating. The bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour.
So this is a real case lah.
The bridge oscillating in one of its natural modes of vibration with a period of 5 seconds.
So resonance is something like this lah. So once something harmonized with the object, as per this, so a resonance occurs when the natural frequency of an object coincides with the frequency of any vibration. So as per the case, most of the time it will be a bridge. So when the bridge is harmonizing with the vibration being applied to it, then it will move in a very high degree of freedom lah, which means you'll be able to wobble up and down. And this will, in most of the cases, will always cause the bridge to fail. So this sort of resonance you'll always find it at suspension bridge, because the bridge is only connected at the end here and here, or maybe at the pillar, supporting pillar. So that's why a bridge always have a very high degree of movement. So usually you'll find this is when the design isn't up to the standard lah for the bridge. Okay, so you have your sound power, which is power is the rate at which sound energy is produced at the source. So it's usually measured by watts. And then sound is measured by the sound intensity, which is the watts over meter square. So this is the formula in which you are used to measure the intensity of sound. So you have your I equals to P sound power of the source divided by 4 pi r squared. So r is the distance from the source. Then you have another formula, which is the intensity pressure relationship. So you have your I, you have your P, and you have your rho. So this is based on the pressure on top divided by the density of the material and velocity. Then you'll be able to get the intensity of the sound also. So this is just the same lah. This one I and this one the intensity is also both used to get your intensity of the sound. Okay, so for all the formula, don't worry, you'll be given the formula sheet lah for your exam. But for your midterm test, I won't be giving it to you lah, because there's only two question of calculation I'll be giving you. So the rest will be fill in the blank and then true and false question. So for your midterm, I won't be giving you the answers, the formula sheet lah. And some more is also open book lah. So I don't think you need it lah. Okay, so continuing on. So sound, there's two types of threshold to sound, which is threshold to hearing and then threshold of pain. So threshold of hearing is the weakest sound that the average human ear can detect. So which is represented by these two values. And threshold of pain is the strongest sound that the human ear can tolerate, which is at these two values. So threshold of there's a difference between these two, which is threshold of hearing is what is the range of sound that we can hear. And then when it goes to pain, which means that we can only hear up to a maximum of this range of sound. So if you were to exceed that sound energy, you will damage our ear mechanism, which means our ear will break or bleed. Okay, sound is measured in decibel. So it can be in at how high the sound is or how high the pressure is at, and is represented by this formula. So for sound, you have to make use of logarithm to calculate or measure sound. So sound is measured in decibel, and to calculate sound, you have to make use of logarithm. So inside the formula, you have your n, which is a number of decibel, and then you have your intensity of the 2 point being compared, and then also either that or intensity of the pressure being compared. So different different either you can either get your number of decibel from intensity or pressure. So our human ear is very sensitive. We'll be able to detect minute changes, but a changes of 10 dB increase and or decrease will sound very different to us. So that's why we cannot use the normal mathematical way of adding plus and minus, because dB, the increase and decrease of dB makes the sound seems the increase or decrease of the 10 dB makes the sound seems approximately twice as loud or half as loud. Then we have to use logarithm to work out the intensity of the sound. Okay, so we'll be able to hear around this range of sound. If you were to go out of this range, you won't be able to hear anything. So a representative of this is when if you were to be near a airport, if you were to hear a airport taking off and landing, that is at a very very high sound level. So if you were to be prolonged, if you were to be exposed to it in a prolonged period, then we are actually perceiving the noise at the threshold of pain. And then our usual environment is that will be in either in a average classroom at 50 dB. So this is a moderate. So a prolonged hearing of this won't affect our hearing. So this is another formula for the sound intensity level. Is the same about this. And then we have your sound pressure level, which is you have the difference is you have to be multiplied by 20. Okay, so example to this is a sound has a pressure of 4.5 Pascal when measured under the certain condition. So calculate the sound pressure level of this sound. So threshold of hearing pressure is at 20 times 10 minus to the power of minus 6. So you're given your pressure and your hearing pressure. So using this formula, if you were to sub it into here, you'll get your SPL, the sound pressure level at 67 decibel. Another example, so you to calculate the changes in sound level when the intensity of a sound is doubled. So for this, you have to have an initial lah, because you're not given any value. So you have using the formula where you assume the first I as an initial intensity and because it says changes of sound level when sound level is doubled. So you have to assume another 2i, which is the final intensity. So putting them in a formula, you have to move them around lah. And by solving them, you find out that the the to double the energy in a given sound, you just need to increase them by 3 dB. So for logarithm, just a quick rule of logarithm for you guys here lah. I put it in the slides so you can refer back to it on for this chapter. So in logarithm, if it's a multiply inside this, you can move it out and plus them together. If it's a divide, then it's a minus. So it's a power of k, then you can move it to the front and multiply it. If it's 1, it's 0, b, so lah, and so on lah. So this is the rule lah for logarithm. So when the question regarding this topic comes out, you can just refer to this rule and then you work out how to move around the equation lah. Okay, so you have your combination of sound level. So to add intensity is simply just by adding them together. But if you were to add pressure, then you have to square root. You have to add them together. You have to be power by 2, and then you have to add them together, and then you have to square root them. Then you have your fourth example. So to calculate the total sound level caused by the combination of sound level of 95 decibel and 90 decibel, the threshold of hearing intensity is 1 times 10 to negative 12 to the power of negative 12. So given this value, okay, so another additional tips for how to solve this question is if you find that your calculator won't have the anti-lock function, so you need to solve this by using 10 to the power of this x is equal to y. So here you have anti-lock. So to solve it, you have to use these methods lah. So this is a formula. You have to use this SIL equals to 10 log I over IO. The formula, you have to sub in the given factors, which is 95. So by working out this until the end, you're given the threshold of hearing is 1 times 10 power of negative 12. Then you'll be able to get the I, which is at 3.16. So you have to repeat it again and you'll get 2 for one is for 95 decibel, another one is for 90 decibel. So you'll get the intensity is 3.16 for the 95 decibel and 4.16 for the 90 decibel. So by combining them together, you'll get a total sound level of 96 decibel. So this is all moving the formula around and then solving the equation with the formula. So because of how sound wave spread, so from a point source, sound will always try to spread in a constant straight line. Then the total energy of the wave front remain constant, but the area of the wave front will constantly increase. So from point A to point B, they will just keep spreading out. So it's quite same like the way sound spread is quite same like how light spread. So as you can see here is something like the inverse square law. So as the sound travel further and further away from the source, then the sound level will decrease. So the sound intensity from a point source decrease in inverse proportion to the square of the distance from the source. So this relation is expressed in this formula. So I is inversely proportional to the distance. So the closer you are to the sound, the louder it is the sound. So if you were to listen to a music, you want to be as close as possible to the source of the sound or your speaker. And then you have the ratio of any two intensity is given by the formula. So intensity is I intensity 1 over 2 is equals to the distance 2 over 1. So this is the ratio lah. So sound is related to the way of how sound travel is related to the inverse square law. So the further they travel, the less energy they have. So energy twice as far from the source is spread over 4 times the area. So as you move twice the distance, the energy remaining is only 1/4 of the is only remaining only 1/4. So from point A to point B, which means 100 meter to 200 meter, only 1/4 of the energy is remaining, which means they are only 1/4 louder. But dB is peculiar lah, so you won't be able to measure it in normal terms. So another example, so a microphone measured sound at a position in a free field 5 meter from point source. So you have to calculate the change in SIL if the microphone is moved to a position 10 meter from the source. So you're given SPL at distance of 5 meter and 10 meter. So you have to find out the changes of the sound intensity level if you were to move it away from another 5 meter away from this. So using the form, you have to use in the formula. So you're just moving around the formula. Finally, you'll get a 10 log 100 over 25. You'll get equals to 10 log 4. So by putting a log 4 in a calculator, you'll be able to get a dB of about 6 dB decrease. So this is just a movement of the formula lah, and to show you when the distance doubled from 5 meter to 10 meter, you actually get a SPL or the decrease of the sound pressure level at 6 dB, which is if you were to look at it, this is true lah. Like from 100 meter to 200 meter, if you're measuring it at 66 dB, you have a decrease of 6 dB. So this is why how the value is obtained based on this example 5. Okay, so let's just take a quick break, about 15 minutes. You guys have a drink or eat a bit of light breakfast. Okay.